Now, before discussing the definition of rank of a matrix, let's start with some basic points. What will be the ranges of rank of a matrix? Generally, rank is possible even for square matrices and even for rectangular matrices also. Let's start with some basic points. Suppose I have a matrix A whose size is m cross n. So here m can be equal to n or m need not be equal to n. If m is n, then it is called a square matrix. If m not equal to n, then it is called a rectangular matrix. Now at first, let us try to find the rank of a square matrix. Therefore, m value equal to n. Therefore, let us concentrate on rank of a square matrix. Suppose when A is some matrix, its rank is denoted by the symbol. Rank of A is denoted by the symbol row of A. Now, since the dimension of A is n cross n, the lower rank of A is 0 and the maximum rank of A is n. So, these are the various boundaries for the rank of a matrix. Since A is a n cross n matrix, maximum rank will be n and minimum rank will be 0. Got it? I have a n cross n matrix. At first, let us try to find rank of a square matrix. Suppose if A is a 2 by 2 matrix, maximum rank will be 2. Even I will discuss shortly how to find rank of a matrix. So maximum rank will be 2. Suppose if unfortunately if rank not equal to 2, it can be 1. It can be 1. Don't think that if rank not equal to 2, then definitely it will be 1. It may be 1. If rank also not equal to 1, then definitely it will be 0. Therefore, when you deal with 2 by 2 matrix, maximum rank will be 2 and least rank will be 0. So when you generalize this for a n cross n matrix, maximum rank will be n and minimum rank will be 0. Now let us start from bottom to low level. Top to bottom level. So what will be the ranks of a square matrix? Let us start with a simple 2 by 2 matrix. Suppose I have a matrix A equal to 1, 2, 3, 4. Now the size of this matrix is 2 by 2. So as we mentioned just now, the maximum rank will be 2. If rank not equal to 2, it can be 1. Otherwise, it will be 0. Now let us try to see whether this matrix has rank 2 or not. If you want to find the rank of a matrix, you must find the depth of that square matrix. Now here the depth of this matrix is 1 into 4 minus 2 into 3. This is minus 2. It is not equal to 0. Therefore, in this case, the determinant is not equal to 0. Therefore, the rank of this matrix is 2. Now, A is a 2 by 2 matrix whose depth is non-zero. It can be positive or it can be negative. Only thing is you must get non-zero number. So, here it is a 2 by 2 matrix whose depth is not equal to 0. Hence, its rank is 2. So, this is example 1. Now, when you take example 2, suppose the matrix is this. A equal to 1, 2, 2, 4. Now, this is a 2 by 2 matrix. So, maximum rank will be 2. Otherwise, it can be 1. Otherwise, it will be 0. Now, in this case, the depth of this matrix is 0. Just 1 into 4 minus 2 into 2. Or second row is 2 times of this. R2 equal to 2 times of first row. One row is a constant multiple of another row, depth is 0. Since for a 2 by 2 matrix, the depth value is 0, therefore rank should not be 2. Now, since rank not equal to 2, next I will try to see whether this has a rank 1 or not. Basically, that rank represents dimension of submatrix of original matrix. Dimension of submatrix of original matrix. What is a submatrix? A matrix obtained from original matrix by eliminating few number of rows and few number of columns. Suppose I have a 3 by 3 matrix. Now I am eliminating at first row and second column. So the remaining will be a 2 by 2 matrix and that is the submatrix of original matrix, just like set, subset, matrix, submatrix. Okay. So in this case, here rank not equal to 2. So if not equal to 2, it can be 1. Now if you want to say that rank value equal to 1, I must find at least one 1 by 1 submatrix whose depth is not equal to 0. Got it? I must able to find at least one 1 by 1 submatrix of this matrix with the det value not equal to 0. Now let us see. You can start with either this, or you can start with this, or this, or this. Suppose I am starting with this, A1 equal to 1. Now this is a 1 by 1 submatrix. Don't confuse with this one and this one. Or you can select this also, this or this also. So directly I am taking this one. Now in this case, this is a 1 by 1 submatrix of A. What is the det of this A1? This is 1. It is not equal to 0. Now therefore in this case, I got at least one 1 by 1 submatrix whose det is not equal to 0. Therefore the rank of this matrix is 1. Now let us take an example where the rank is 0. Suppose I have a matrix A equal to 0, 0, 0, 0, 2 by 2. Maximum rank will be 2, otherwise it can be 1, otherwise it can be 0. Now in this case, the determinant of this matrix is 0. Since its det value is 0, rank cannot be 2. Now let us try to find whether it has a rank 1 or not. Here this is a 1 by 1 submatrix of A. 1 by 1 submatrix, 1 by 1 submatrix, 1 by 1 submatrix. So in this case we have 4 1 by 1 submatrices. And unfortunately every 1 by 1 submatrix of this A has 0 det value. To get a rank, I must be able to find a submatrix with a non-zero det value. But in this case, unfortunately, every 1 by 1 submatrix has 0 det value. Therefore, every 1 by 1 submatrix has 0 det value. Therefore, rank cannot be 1. So ultimately, rank not equal to 2, rank not equal to 1. So ultimately, it is 0. So in this case, we are getting rank 0 because it is a null matrix. Therefore, from example 3, we conclude that rank of A equal to 0 if and only if A is a null matrix. If and only if A is a null matrix. So the meaning of this is, if rank of A is 0, definitely it must be null matrix. If there is a null matrix, definitely its rank will be 0. It means that if a matrix contains at least one non-zero number, then its rank will be at least 1. Is this point clear? I have a matrix A, say for example 3 by 3. So in a 3 by 3 matrix, we have 9 entries. Out of all these 9 entries, if at least one entry is non-zero, definitely its rank will be at least 1. So therefore, the consequence of another point is, this is one not. And second point is, if A is not a null matrix, then rank of A is at least 1. That we can write it as rank of A is greater than or equal to 1. Now, from all these examples, we can conclude how to find a rank of a matrix, and even we can say what is the definition of rank of a matrix. Now come back to all these examples. Now in this case, in the very first example, let us start with 2 different dimensions. Now this is a 2 by 2 matrix. So one possible dimension of its submatrix is 2 by 2. We know that every matrix is a submatrix of original matrix. So what is the 2 by 2 submatrix of this? That is itself. So what is its dimension? 2 by 2. What is the next possible dimension? 1 by 1. Now it is a 2 by 2 submatrix whose det value is not equal to 0. See, I always want dimension whose det is not equal to 0. Now in this case, this is a 1 by 1 submatrix whose det is not equal to 0. Therefore, in the first example, I got 2 different dimensions with a non-zero det value. One is 2 by 2, another is 1 by 1. Out of these 2 dimensions with a non-zero det value, 2 is the largest dimension. That's why the rank is 2. Now when you look at this, in this case I am getting only one dimension, that is 1 by 1. So therefore that could be the largest, therefore rank is 1. Therefore the rank of a square matrix is defined as the largest possible dimension of submatrix of A with a non-zero det. I repeat once again, the rank of a square matrix A is defined as the largest possible dimension of submatrix of A with a non-zero det value. Right? Write the definition. Let A be any square matrix. Let A be any square matrix. So the largest possible dimension of submatrix of A with non-zero det. The largest possible dimension of submatrix of capital A with non-zero det is called rank of A. It is denoted by row of A. It is denoted by row of A. Next, note. If A is any n cross n matrix, then 0 less than or equal to row of A less than or equal to n. 0 less than or equal to row of A less than or equal to n. Examples. Example 1. A equal to 1, 2, 3, 4. 2 by 2. Det A equal to minus 2, not equal to 0. Therefore, rank of A equal to 2. Next, example 2. A equal to 1, 2, 2, 4. 2 by 2. Det A equal to 0. Therefore, rank of A not equal to 2. Det A equal to 0. Therefore, rank of A not equal to 2. Next, A1 equal to 1. You can write any one of these numbers. I am starting with 1. A1 equal to 1. 1 by 1 is a submatrix of A with non-zero det. Is a submatrix of A with non-zero det. Therefore, rank of A equal to 1. Rank of A equal to 1. Now, come back to last example. A equal to 0, 0, 0, 0. Det A equal to 0. Therefore, rank of A not equal to 2. Next, every 1 by 1 submatrix of A, has 0 det. Every 1 by 1 submatrix of A has 0 det. Therefore, rank of A not equal to 1. Therefore, rank of A not equal to 1. Therefore, rank of A equal to 0. Rank of A equal to 0. Note. First note. Rank of A equal to 0 if and only if A is a null matrix. If and only if A is a null matrix. Note 2. If A is not a null matrix, then rank of A is greater than or equal to 1. Then rank of A is greater than or equal to 1. Now let us recall these points. Now from all the three examples, one can easily make some comments. Let me ask you a few questions. Suppose I have a 4 by 4 matrix. I am saying that its rank is 2. I have a 4 by 4 matrix. I am saying that the rank of this matrix is 2. It means I can make three different comments. The first comment is its det is 0. And second one is every 3 by 3 submatrix of A has 0 det. Third point is there is at least one 2 by 2 submatrix whose det is not equal to 0. I repeat once again. The point is this. I have a 4 by 4 matrix. I am saying that its rank is 2. It means that point number 1, its det is 0. Point number 2, every 3 by 3 submatrix of A has 0 det. Point number 3, observe this. This is very, very important. There is at least one 2 by 2 submatrix whose det is not equal to 0. Therefore, its rank is 2. Therefore, if you want to say that rank of a matrix equal to some number, it is very simple. But if you want to say that rank of this matrix is not equal to 3, it means that you need to put lot of efforts. I have a 7 by 7 matrix. I am saying that rank not equal to 3. Got it? Or I am saying that I have a 4 by 4 matrix. I am saying that rank not equal to 4. That means that is 0. I am saying that rank not equal to 3. That means every 3 by 3. Because in this case, I will get multiple number of 3 by 3 submatrices. Got it? So therefore, if you want to say that rank of a matrix is certain number, it is simple. But if I want to say that rank not equal to this number, I need to put lot of efforts. Right? Now, based on the experience what we had in this session, let us write the procedure to find rank of a square matrix. Right? Yesterday, procedure to find rank of a square matrix. Procedure to find rank of a square matrix. Now suppose I have a n cross n matrix. Now let us discuss this procedure in terms of steps. Now since it is a n cross n matrix, maximum rank will be n. Now here rank of A equal to n if det A is not equal to 0. This is very clear. So whenever there is an n cross n matrix whose det is not equal to, its rank will be n. Otherwise means rank not equal to n. If rank not equal to n, there is a chance to get the next possible dimension. The next possible dimension is this number minus 1. So rank of A equal to n minus 1 if there is at least one n minus 1 cross n minus 1 submatrix of A with a non-zero det. With a non-zero det. Now let us try to understand point number 2. Here at first rank equal to n when if det A not equal to 0. Suppose if it doesn't happen, then the next possible rank is n minus 1. Just come from top to bottom level. If rank not equal to 4, there is a chance to get rank value 3. If there is no chance to get rank 3, then there is a chance to get rank 2. Otherwise it may be 1. Otherwise it is 0. So first 4, next 3, next level 2, the next level 1. In the last level it will be 0. I am verifying same thing by taking general value of n. So rank is equal to n minus 1 if there is at least one n minus 1 cross n minus 1 submatrix of A with a non-zero det. At least is important. Suppose assume that this is also not happening. Otherwise, so the next possible rank is n minus 2. So rank of A equal to n minus 2 if there is at least one n minus 2 cross n minus 2 submatrix of A with a non-zero det. With a non-zero det. So in this manner, we always find the rank of a square matrix. Rank equal to n. Otherwise it can be n minus 1. Otherwise it can be n minus 2. Like this we continue the procedure until we get a submatrix with a non-zero det is identified. Got these points? Note all these points. Like this, the procedure is repeated. Like this, the procedure is repeated until a submatrix with a non-zero det is identified. Like this, the procedure is repeated until a submatrix with a non-zero det is identified. I think this is very clear. So one can easily find rank of a square matrix using this particular procedure. Now let us try to find the rank of a rectangular matrix using the same procedure. More or less, of course, there will be some changes. Let us make some modifications to this procedure so that we can easily find rank of a rectangular matrix. Now, before going for some comments, some changes in this, let us start with some general example. Suppose I have a 2 by 3 matrix. So, for example, 1, 2, 3, 2, 4, 8. So, the size is 2 by 3. Now, as we know that rank value always depends on det value. But this is not a square dimension to find its det value. So, what I need to do is, here one column is excess. So, therefore, that means one row is lagging. So, I may introduce one row, or one column is excess, or I can eliminate one column. So, here introducing lagging number of rows or introducing lagging number of columns makes some different scenario. So, let us do not follow that. Here one column is in excess when compared to rows. So, try to eliminate columns wise. Therefore, when you look at 2 by 3 matrix, maximum rank will be 2. Otherwise, it is 1. Otherwise, it will be 0. So, maximum rank will be 2. Otherwise, it can be 1. Otherwise, it will be 0. Now, let us see in this case. So, let us go for finding determinants of 2 by 2 submatrices. Here, one submatrix is this. A1 equal to 1, 2, 2, 4. Now, this is a 2 by 2 submatrix, but its det value is 0. Therefore, this A1 is not useful. But with this, don't conclude that rank not equal to 2. Because in this case, there are multiple number of 2 by 2 submatrices. See, in the previous case, when we gone through procedure to find rank of a square matrix, if det of that matrix is 0, then rank not equal to that dimension. But in this case, it is a rectangular matrix, size is 2 by 3, maximum rank will be 2. Because one column is excess, eliminate columns. At first, eliminate third column. For example, 3, 8. If I eliminate third column, I am getting a 2 by 2 submatrix of this. What is the det of this? Its det is 0. But with this, don't conclude that rank not equal to 2 because there are multiple number of 2 by 2 submatrices in this. Now, let us go for A2. A2 equal to, for example, I am eliminating second column. Then I will get 1, 3, 2, 8. Now, the det of this matrix is 1 into 8 minus 2 into 3. This is 2, not equal to 0. Therefore, in this case, I got at least one 2 by 2 submatrix whose det is not equal to 0. Therefore, the rank of this matrix is 2. The rank of this matrix is 2. Similarly, suppose if I take a 7 by 4 matrix, 7 by 4. Now, number of rows is excess. So, therefore, whenever there are number of rows in excess position, eliminate those number of rows to make square dimension. Got it? Because the rank value always depends on det value. So, when you deal with 7 by 4 matrix, 3 rows are in excess. So, eliminate 3 rows. First, you select 3 from 7. So, as many rows you can eliminate, but exactly 3 rows has to be eliminated. So, whatever the rows you are eliminating, that is immaterial for us, but you need to eliminate exactly 3 rows. So, when you eliminate 3 rows, the matrix dimension becomes 4 by 4. In that way, you will get multiple number of 4 by 4 submatrices. Say, let me work out this. Suppose I have a 7 by 4 matrix. Now, in this case, 3 rows are excess. So, eliminate 3 rows. So, when you eliminate 3 rows from these 7 rows, the matrix size becomes 4 by 4. So, if you want to eliminate 3 rows, first you select 3 from 7. So, this can be done in 7C3 ways. So, 7C3 is 7 factorial by 7 minus 3 factorial, 4 factorial into 3 factorial. This is 7 into 6 into 5 into 4 factorial divided by 4 factorial into 3 factorial. And this is 4 factorial will get cancelled. So this is 35. What this count represents, when you take a 7 by 4 matrix, here 3 rows are excess. So my next choice is elimination of 3 rows. So if I want to eliminate 3 rows, I must select which rows I need to eliminate. So therefore select 3 from 7. This can be done in 7C3 ways, combinations. Select 3 from 7. Once you select 3 from 7, eliminate those. The next dimension becomes 4 by 4. Therefore, when you take a 7 by 4 matrix, you will get exactly 35 submatrices with the dimension 4 by 4. Out of all these 35 submatrices with the dimension 4 by 4, if at least one has a non-zero debt value, then its rank is 4. Otherwise, go for 3 by 3 submatrices. Then eliminate 4 rows. Eliminate 1 column. Then you will get 3 by 3 submatrices. Many number of 3 by 3 submatrices. Out of all these 3, if at least one has non-zero debt value, then rank is 3. Otherwise, you next go to 2 by 2. Next 1 by 1 like this. Therefore, when you take a 7 by 4 matrix, maximum rank will be 4. When you take a 2 by 3 matrix, maximum rank will be 2. Therefore, when you take a general M cross N matrix, when you take a general M cross N matrix where M not equal to N, then maximum rank will be P, where this P is nothing but minimum of M comma N. Where this P is nothing but minimum of M comma N. Got it? This is the only change in this, except that the procedure is almost same as this particular procedure. So when you take a 2 by 3 matrix, maximum rank is 2. If it is 7 by 4, maximum rank is 4. So when you generalize for general M and N values, for a general M cross N matrix where M not equal to N, maximum rank will be P, where P is minimum of M comma N. Now let us make changes in this procedure. Suppose I have a M cross N matrix where M is not equal to N and P equal to minimum of M comma N. Here this is procedure to find rank of a rectangular matrix. So here let A be any M cross N matrix with M not equal to N and P equal to minimum of M comma N. Therefore, rank of A equal to highest rank will be P if there is at least one P cross P submatrix of A, one P cross P submatrix of A with a non-zero debt. Otherwise, if rank not equal to P, the next possible rank will be P minus 1. So rank of A is P minus 1 if there is at least one P minus 1 cross P minus 1 submatrix of A with a non-zero debt. Otherwise, rank of A is P minus 2 if there is at least one P minus 2 cross P minus 2 submatrix of A with a non-zero debt. So in this manner, we can find the rank of a rectangular matrix. Hope these points are very clear to you, right? Note all these points. Like this, the procedure is repeated. Like this, the procedure is repeated until a submatrix with a non-zero debt is identified. Like this, the procedure is repeated until a submatrix with a non-zero debt is identified. Now let us work out with 2 to 3 different examples on rank of a rectangular matrix. Let us start with this example 1. A equal to 1, 2, 3, 2, 4, 8. So here its size is 2 by 3. Now directly you can start with this. this 2 by 2 submatrix 1, 3, 2, 8 whose det is not equal to 0. Therefore, from this it is clear that the rank of this matrix is 2. Now, let us take one different example. Suppose I have A equal to, let us start with the 3 by 4 matrix, 3 rows and 4 columns. Or for example like this. This is 1, 2, 3, 4. For example 2, minus 1, 0, 8. For example 3, this is 1, 3, this is 12. And this one is 5. And this is 0, this is 3 and this is 20. Of course, it becomes 4 by 4. Let us eliminate one row, one column. For example, the matrix is this. Now, you can see the size of this matrix is 1 row, 2 row, 3 row, 4 rows. So, it is 4 by 3 matrix. For a 4 by 3 matrix, maximum rank will be 3. Therefore, try to eliminate one row at a time. So at first I will try to eliminate the row like this. Suppose I am getting matrix A1 by eliminating first row. So just eliminate first row. So you will get remaining matrix with these rows. So minus 1, 0, 8 and 1, 3, 12, 0, 3, 20. Now you can see this is a 3 by 3 submatrix. So here what is the det of this matrix? The det of this matrix is 0 because in this case R3 equal to R1 plus R2. That is, there is a linearly dependence relationship among rows. Minus 1 plus 1, 0. 0 plus 3, 0. 8 plus 12, 20. Therefore, in this case, the det value is 0. But with this, don't confirm that rank not equal to 3 because there are multiple number of 3 by 3 submatrices in this case, right? Now, I will go for this A2. A2 is a 3 by 3 submatrix of this by eliminating only second row. So therefore, keep first row as it is, eliminate second row, keep third row, this is 1, 3, 12 and this one is 0, 3, 20. 0, 3, 20. Now let us try to find the det of this matrix. So in this case, determinant of A2. So you can expand by using first row or second row or by third row. Now this is plus, minus, plus. So therefore this is 2 times det of this submatrix. 3 into 20, 60 minus 3 12, 36. Minus 3 into det of this black. So this is 1 into 20, 20 minus 0 into 12. Plus 4 into det of this. The det of this is 3 minus 0. So therefore this is 2 into 24 minus 60 plus 12. Now this is 48 plus 12 minus 60, even its det is also 0. Its det is equal to 0. Therefore in this case, the det of this 3 by 3 submatrix is also equal to 0. So with this also don't confirm that rank not equal to 3 because there are 2 more submatrices with the size 3 by 3. Now here I will take A3. So A3 is the 3 by 3 submatrix by eliminating only third row. So therefore this is 2, 3, 4, minus 1, 0, 8 and 0, 3, 20. 0, 3, 20. Now let us expand that value. So det of A3. So this is plus, minus, plus. So 2 into, this is 0 minus 24, minus 3 into, minus 20, minus 0, plus 4 into, minus 3, minus 0. Therefore, this is minus 48 plus 60 minus 12. Now its det also equal to 0. Therefore, till now we have identified 3 by 3 submatrices whose det is equal to 0. Now we have another chance. Just eliminate only fourth row. So therefore, when you eliminate fourth row, suppose At first I eliminated first row. Its det is 0. Next second row. Next third row. Next eliminate only fourth row. So I will get a 3 by 3 matrix. This is A4. Now A4 is a 3 by 3 submatrix by eliminating only the last row. Now this matrix is A4. So therefore in this case you can see 2 plus minus 1 1, 3 plus 0 3, 4 plus 8 12. So therefore in this case also the det value is 0. Therefore in this particular example every 3 by 3 submatrix has det value 0. We got 4 different 3 by 3 submatrices in this example, but for everything the det value is 0. Therefore the rank of this matrix is not equal to 3. So if rank not equal to 3, the next possible rank is 2. The next possible rank is 2. Now let us see in this case, suppose if I take this is a 2 by 2 submatrix of A with a non-zero det value. So for example I am taking A5. A5 equal to 3 4 0 8. This is a 2 by 2 submatrix of A whose det is 24. This is not equal to 0. Therefore, I got at least one 2 by 2 submatrix whose det is not equal to 0. Therefore, the rank of this matrix is 2. So, like this, you can find easily the rank of even rectangular matrix also. Please note down this example. So here write the point. Here every 3 by 3 submatrix of A has 0 det. Here every 3 by 3 submatrix of A has 0 det. Therefore rank of A not equal to 3. But there is one 2 by 2 submatrix of A with a non-zero det. There is one 2 by 2 submatrix of A with a non-zero det. Therefore rank of A equal to 2. Rank of A equal to 2. Now let us try to establish one relation between rank of A and rank of A transpose. Whether the matrix is square or rectangular, we can discuss its transpose. So even if it is square or rectangular matrix, since we can discuss its rank, one important result is rank of A is always same as rank of A transpose. Rank of A is always same as rank of A transpose. Just even when you transpose the matrix, rank doesn't affect. So even if it is square matrix or rectangular matrix, rank of A is always same as rank of A transpose. Note this point. Note rank of A equal to rank of A transpose. Rank of A equal to rank of A transpose. So in the examination, if they ask you to find the rank of a square matrix or rectangular matrix, if the dimension is very complicated, definitely there will be some connection among rows as well as some columns. See, always you focus on 2 points. See, rank is almost equivalent to determinant of a matrix. If you want to get the rank of a matrix, determinant plays very important role, right? So therefore, in the future when you want to find determinant of a matrix where the dimension is complicated, just look at the observe the rows or columns. Is there any linearly dependence relation among rows or columns? Suppose if you ask me what is the rank of this matrix, the matrix is this. Suppose 1 2 3 2 4 6 3 6 9. Now this is a 3 by 3 matrix. For a 3 by 3 matrix, maximum rank will be 3, otherwise 2, otherwise it is 1, otherwise it will be 0. Now let us see. Here R2 equal to 2 times R1. Therefore, there is a linearly dependence relationship among rows. Therefore, the det of this matrix is 0. Since this det value is 0, rank not equal to 3. Now, let us see whether this matrix has rank 2 or not. Here, my claim is its rank is also not equal to 2, because when you look at first two rows, there is a connection. Even when you look at first and last rows, there is a connection. This is third row is 3 times of first row. 1 into 3, 3. 2, 3, 6. 3 into 3, 9. Therefore, in this case, another connection is this R3 equal to 3 into R1. So, there is a connection between first two rows. There is a connection from between first and last rows. Indirectly, there is a connection between last two rows also. Multiply second row with 3 and multiply third row with 2. That means you will get 3 times of R2 equal to 2 times of R3. Therefore, R2 equal to 2 by 3 into R3. So, therefore, in this case, because of this point, there is a connection between first two rows, connection between first and last rows, connection between last two rows. That means indirectly, it means that every 2 by 2 submatrix of A has 0 det. Every 2 by 2 submatrix of A has 0 det. Therefore, here rank value, det value 3, 0, rank not equal to 3. And because of these three results, I can say that rank also not equal to 2. But there are certain non-zero numbers in this case. Say, for example, I will take A1 equal to 3. This is a 1 by 1 submatrix of A whose det is non-zero. Therefore, the rank of this matrix is 1. So, therefore, when the dimension of a matrix becomes so complicated, just try to observe rows and columns. Is there any connection among rows or columns? Definitely in the examination, if the size of a matrix is complicated, definitely there will be some connection among rows or columns. Just you try to identify that connection, then immediately you can get the rank or determinant of such matrices very, very easily, right? Even you note this point, note this one example also. Now let me ask you one question. In the previous sessions, we have discussed orthogonal matrix definition, invertible matrix definition. So based on that, we can easily get the inverse of an orthogonal matrix. What is orthogonal matrix? If a matrix is multiplied with its transpose, even in the reverse direction also, you will get identity matrix. That means the orthogonal matrix definition is this: A into A transpose equal to A transpose into A equal to I. This definition resembles identity invertible matrix definition. The invertible matrix definition is this: A into B equal to B into A equal to I. This is the definition of orthogonal matrix, and this is the definition of invertible matrix. From the second equation, easily we can say that A inverse equal to B. Now therefore, in place of, when you observe first equation, in place of B, it is A transpose. Therefore, if something is an orthogonal matrix, then its inverse is given by A transpose. This is most important point. So if something is an orthogonal matrix, its inverse is simply its transpose irrespective of its size. Just note this point also. If A is an orthogonal matrix, then A inverse equal to A transpose. If A is an orthogonal matrix, then A inverse equal to A transpose. Right. Now this is the end of this particular session. Thank you so much.